Am I audible?
Yes, madam.
Let us start the day 6. Good evening to dear participants. It gives me a great pleasure to cordially invite all the participants for the day 6 of ATAL FDP online, which is having the sessions 11, 12 and 13. Now let us invite Mr. Y. Madhu to kindly address the participants and share his reflections on the distinguished contributions of Dr. A.B.V. Kiran Kumar. So, Mr. Madhu sir, over to you.
Yes, ma'am. Thank you, Dr. Saraswati, ma'am. Good evening, everyone. It is my privilege to introduce our distinguished speaker, Dr. A.B.V. Kiran Kumar Garu, an accomplished scientist, entrepreneur, and academic leader in the field of nanotechnology and organic chemistry. Dr. Kumar holds an MSc and PhD in organic chemistry, followed by a postdoctoral specialization in nanotechnology from South Korea, and has also completed a management program at IIM Kozhikode. With nearly 2 decades of research and professional experience, he has made remarkable contributions to the synthesis and applications of nanomaterials and biomaterials, particularly in areas such as flexible electronics, sensors, supercapacitors, wound healing biomaterials, and nano antibiotics. He is the managing director and CEO of Olive Nanotech Private Limited, where he leads innovative product development and consultancy services, bridging the gap between cutting edge research and industry applications. Previously, he served as an assistant professor at MIT Institute of Nanotechnology, MIT University, Noida, and has built strong research collaborations with institutions in India, Korea, and China. Dr. Kumar's academic contributions include 42 research publications, 21 conference presentations, 3 patents filed with 1 granted, and a book chapter. His work has been widely recognized with over 823 citations and an H index of 15. Beyond his own achievements, he is a passionate mentor who has guided numerous MTech, BTech, and voluntary research scientist students. On behalf of KPRIT COE family, we are honored to warmly welcome Dr. Kiran Kumar Garu, who will now share his expertise and insights with us. Dr. Kiran Kumar, sir.
Yeah, thank you. Let me share my screen first, then where to share my screen. One moment. Let me share first. Right. Thank you. Nice, nice, nice. So, right now, so it's clearly visible to everyone, right?
Yeah.
Yes, thank you. Thank you. Yeah, good evening to all. Welcome to another session of mine because I had that second session, I think the second day of that one second day. Then today, I hope you has enjoyed with my lecture and my previous session. So today also I try to give you the more information that's relevant to the your FDP program. And then I'm really honored to have here and that given opportunity from the college and all these things. I really thank to the college and efforts they have given to conduct the 6-day program, FDP program. Okay, so today I'm going just now. Okay, it's almost I think everybody joined. I think I'm going to start my session. Here I have seen. I would like to before entering that my lecture. If anybody wants to know much about this title page image, so there is just you can Google it in YouTube. You can see the link. There is a link here. You can see how we are making issues by using plastics because we are feeling always we are more comfort by using plastics, but that usage of plastics becoming fatal to many environmental as well as aquatic, even animals also. Okay, so please go through, and I will request you all again. So try to change our day habits to replace plastics with you can say that one is metal or even cloth based or biodegradable products. And now we are going to start our today's presentation. Now today's presentation, what is this? I got to, so okay, one moment. Okay, so wait, yes. So today's session on particularly removal of microplastics in industrial effluents. So before that, to understand that what exactly industrial effluents, how they process, will, and based on that, what are the outcomes we are going to get from that today's presentation here. Understanding the process of industrial wastewater treatment, and second one, how this treatment affects the microparticles removal from the industrial wastewater. Then what kind of modifications they have done for the conventional water treatment plants. And then and finally, we will go to for overview of the few advanced physical, chemical, and biological techniques which are under research, and few of them things still we can able to adopt to the industrial applications, but still most of the cases we can say that those advanced methods still under the research. Next slide, we have industrial water treatment. What exactly industrial wastewater treatment? As we know that one, sludge removing from wastewater in bulk scale is not easy. It's very complex, and we can say that one the mechanical issues. There are a lot of things. So there are many stages. Among that, there are four stages are main important stages are there. So they use generally physical, chemical, and biological processes to remove these contaminants. And then key stages are preliminary treatment, their screening and grit removal. And second one is primary treatment, sedimentation, dissolved air flotation, secondary treatment, biological degradation. They use that one. And then we can say that with the tertiary treatment, we can say this is an advanced treatment where we can able to include our advanced removal technology for microplastics. So now first come to the first things. What is the process stage? What exactly will happen? The pre-treatment. That's called pre-treatment or preliminary treatment. So here you can able to see up. There are two pictures in this slide. So in in the second picture, you can see there are screen, and then you can see the grid chamber and the sedimentation tank. So these are the three stages and three steps. So in the first stage, you can use a screen, and you can see the left-hand side of the picture. It's very common in everywhere. They fix a screen to filter the large scale debris, whatever it may be, it is or plastic or any wood or any other materials, whatever it may be. So to remove that one, this is this our effluent uh, first has to enter into the and through this screen only. So that's a thing. Next, well, after completion of this process, the water they allow into the grid chamber. So what is this grid chamber? The grid chamber is nothing but a tank, simpler tank. Why this importance of this grid chamber? See, in our wastewater treatment, particularly in industrial or even in the municipality industrial water treatment. So now, along with these small and big size particles, we also have the cinders, the stones, sand, everything will come along with this water flow. So that's why, and second stage, we will try to remove this grit, everything from the grit chamber. So here you can see this is a in the right hand side picture. You can see this inlet, and then this is a vortex based. There are many kinds of many types of that grit chambers are there. There are rectangular chambers, and but this is the most uh, of places they use this one, then because this is one of the most effective grid chambers. So in the second stage, the water that should flow along to flow through this grid chamber. So while they are flowing, the agitator is there. So due to that one, all that's high density particles, means like sand and stones and all this water it may be. So they settle down the bottom, and then they simply collect these particles. Now, come to the point. So we have removed very large scale materials from our wastewater in the process stage by using a simple screen. And second stage, we use a filter type. We can say that one, a filter type, a conical flask type, a funnel type chamber. So we use that one. So that there we able to remove that high density particles where they will get rid of that solution. And now, so there are two kinds of particles are still there in our water flow. So those are suspended particles and then along with the fats, oils, and grease. Now, so one more thing is going to add, that is our macroplastics also are going to still there during this process. Now, come to the point here. Here, this what happens. So, if you want to remove, can you able to remove the microplastic? At least some size of the microplastics I can able to remove in this stage or after this stage. Yes, it's possible. So, this is not the general. They're not using in general purposes or general things. This is very specific thing. So, in few countries only they are using because since wherever they have strict regulations to remove of the microplastics from the serious water, there only things still some industries only they are using this. I don't think so everybody are using these procedures in common things. So now come to this point here. Here what they do that one, so they use a stack of sieve pans. Here you can see that one. So they use a stack of sieve pans. It's simple. It's nothing but a filtering. Again, it's another type of filter. So they use that one. Here you can able to remove if here this, since it's a stack of sieves has that filtration process, the different size of pores, you can able to remove that microplastics. Is not only some different sizes for suspended particles and microplastics also. But the problem is arises here. We can say that 500 microns are around there's a limitation of the sieve size. Due to the limitation of the sieve size, we can't able to remove much smaller microplastic particles here. We can say that a meso size of the microplastics here, meso-sized mesoplastics. Now, come to the point. Can we able to remove even that such type of large plastics? Means maybe due to its irregular shapes and even the fiber type plastics fibers we can't able to remove from the sewage water at this stage. So this is the modification of the general effluent systems. Next, it is the first modification. And next stage, we go to the primary treatment. This is one of the most important section in any effluent treatment plants that is called sedimentation process. So what they do in the sedimentation process? So here they simply, what we have done here, simply there is a screen and then for the remove the microplastics, they simply enter into the grid chamber, and then here and here we have introduced another thing, that is we can say that simple microfiltration process. We can say that one. Now after three stages, this effluent enters into the sedimentation tank. So these sedimentation tanks are very big tanks by volume or size. They are very big in this plant. Then allowing the heavier solids to settle down the bottom of forming primary sludge. So here the first actual filtration starts, we can say that one. So what happens that there looks like, okay, yes. So it might be, you might have seen that. Oh, I think I don't have that. No, I should. Okay, so here you can see this one. This is the cross section of the chamber. What will have this chambers? This is actually a little bit slow process. Here you have this is a inlet. You can here. Okay, this is the inlet, and it comes here, and this is outflow like this, outflow like this, and then this is very slow process. They control that fluid movement. It's very slow, in very slow manner they controlled. And then here you have that, you can see this float box. You can able to see this float box. I will explain in the coming slides about this one. What's the importance of that one? Here you can see that we noted where, what it have, what's the help of this one. Here, general, we can say that V-shaped cones, we use the measure the flow rate of the fluids. So here, based on that, they try to control the speed, because we need to give enough time to settle down the particles there. And now come to this point, and then this next. So, and here other process, sedimentation is one step here. It will take simultaneously. Skimming process also will take here. Yes, here the skimming process also, they do this one. So these two important steps will happen in this stage. What is the skimming? The skimming is nothing but a floating particles. Sometimes they introduce the air also to improve these particles. That is called. That's why you can able to see this one. This is a the scum outlet, and then you can able to see this. Scum box with beach plate. This is a scum batch, and we can able to see the scum here. And then the fourth, that whatever is light density particles, they all are due to the slow process. What they happen, the high density particles are slowly settled down at the bottom, and the low density particles are fourth. We can say that everything that comes to the surface of the water. So that's we call scum. So there is a separate setup to remove this scum from scum. That's why it's called scum box, and this is the scum outlet. So this the process. In some cases, even they use that air inflow to improve this scum formation, improve the scum formation as well as, but it's not common for all treatment plants. Now, this what happens in this section. So we can see that after removal of the big objects, the sewage can contain suspended solid particles and organic, inorganic materials. Chemical pre-treatment also they do here. Chemical pre-treatment process like pH regulation, chemical precipitation, and de-oiling, everything happens. Approximately 20 to 50% of incoming biochemical oxygen and 50 to 70% of the total suspended solid objects and 60 to 70% of oil, grease are removed during this primary treatment process. And now some organic compounds made from nitrogen, phosphorus, heavy metals carried out with solid objects are thrown out during the primary sedimentation process. Okay, so most of the cases I have seen that one, even in Amita University also, we have up to this plant, I think they used to use that treated water for the plantation purposes. So, okay, now come to this next stage of this one. So, what's the effect of this treatment on microplastic removal? So now come to the point, the primary, preliminary and primary treatment would effectively remove the majority of the microplastics with simple modifications. We can say that one. And then approximately 30 to 59% microplastics could be removed during the preliminary treatment, as well as 50 to 98% microplastics were removed after primary treatment. Means if you're talking about the size only, the largest size, we can say that one. The large size microplastics can be easily removable with the simple modifications in the industrial effluent treatment plants. Now come to the point. The skimming. So removing these particles, so skimming, as I told you that this is called skimming process, removing that's a scum formation and removal that's a skimming process. The skimming process is most crucial during this process. Oh, yes. So that's a thing. Even that microparticles, we can say that high density microparticles can get sediment at the bottom of the tank along with that grit and other things, that one. So we can say in these two ways. That's why we can say that one preliminary and primary treatment can able to remove the maximum number of microplastics with larger size to meso, up to we can say macro to meso size microplastics we can able to remove that one. Now come to this one, next one. I'm coming to this. This is already done. Now come to this one, secondary treatment. So what is the secondary treatment? The secondary treatment here, they introduced into the activated sludge process. This is another step here, where here also we are going to get the solids, the biosolid sludge that called. Here they introduced into aerobic bacteria into the wastewater tank to degrade the organic pollutants, converting into the biomass. We call biosludge also, we call that one. So this mixture flows to secondary carrier where the achieved sludge settles out by the gravity. So sometimes to improve this process, here this aeration tank is must because we need to allow to grow this bacteria. So the bacterial growth purposes, the aeration tank is a must here. And then due to this process, because this is also a little bit slower than that earlier process here. Now come to this point. So these are the secondary treatment to further clarify effluent from primary treatment to remove organic and inorganic suspended particles. And then aerobic, we know that an aerobic bacteria and anaerobic bacteria, so they can able to degrade the organic pollutants as into the end products as carbon dioxide, ammonia, and general water. So that's why in that during that process, the tanks gives a very bad smell. You can say that one. And several aerobic biological treatments are necessary as secondary treatment, differing primary in the manner of oxygen suspended microorganisms. So organisms metabolize the organic. Secondary treatment is essential. That's gone. Now come to the next slide. So this is the last step. We can say that one. This is the last step in where it is. Yes. Sorry. Last step in the after that primary and to collect the sludge. So because here this the last stage where we can collect all the sludge in the first primary and secondary stage. But here there is a problem for us where our microplastics are going. So we are simply removing them, but we are can't able to remove from the environment. So this is the problem. How we are treating this sludge? Generally in this sludge tank, and then they put into the open surface, and they get dried. So what we are going to use most of the cases, this sludge they simply transferred to the fields, agricultural fields sometimes also. So this is the problem. So how reaching to the water bodies means we are simply able to treat the our industrial effluents, but we can't able to degrade the plastic microplastics in that sludge which is located in the sludge. Here is the overall process. You can say that one of the first stage and second stage. I can say that one. This is the grid chamber and the primary settlement and aeration tank and second settlement outflow. This is the things. Now come to the another step. This is the tertiary treatment. So tertiary treatment is not common for all industrial effluents, but sometimes depends upon that. I already told you one. So depends upon that what kind of industry that is and what kind of effluents we are getting. That based on that, people should use depends upon the regulations. Some industries should do the tertiary treatment also. What is this tertiary treatment? So this tertiary treatment is based on a filtration process where the effluent treated from the secondary treatment processed, and in this treatment, effluent targeted again to get good quality before releasing to the environment. This is the most important point. So whether we are doing or not, I'm not clear about that. Our government policies, how strict they are to run this tertiary treatment process during the effluents and to remove that things. So I can share that one as during my visit of the this pharma industries. I used to observe the bad odor around that effluent plants and even some soil coloration. I don't know what's the exactly our government policies and which kind of treatments the industrial people follow because they don't give us full details. Now, what exactly this tertiary treatment? This tertiary treatment is nothing but we can say that is more now once the completion of the effluent, the first and second stage or third stages. In this fourth stage, we can able to remove the minute particles. We can say that this tertiary treatment is must for removing of the microplastics from the water. You can say that one. So here you can able to see this one. There is a filter. There is a layered filter. We can see that whatever that depends upon that requirement, they use that filter material to maintain the pore size. So this is a recycle again and again. We can do that one. Because this is a two-way process. If you want to do it again you can come backside or from backside again. We can repeat the process. Once or twice, depends upon the quality, which quality you want to do, or finally effluent. So this advanced tertiary, what kind of advancements can apply in this tertiary treatments are membrane filtration, advanced oxidation, adsorption, and disinfection. Generally, most of the cases in our household microfilters, we use these disinfections and UV light to break down and then this membrane filters, household purposes, or milky waters or mineral water for manufacturing purposes only. The advanced treatment, tertiary advanced treatment plants, they use that one. So in general, the industries, they don't use this advanced tertiary treatments. Why? We'll discuss in the coming slide. So what kind of filtrations they use that in membrane filtration means ultrafiltration, nanofiltration process, and reverse osmosis, use of membranes to remove dissolved salt and heavy metals. And then what is the advanced oxidation? In general, advanced oxidation, they use ozonization or UV light even in a household filters also to kill the pathogens most of the cases. And then adsorption. Absorption the carbon filters, they use activated carbon filters, they use to remove the specific residual organics and contaminants. And then disinfections. Oh yeah, same. They use that, but in large scale, they use chlorination earlier. And then, but if you're talking about household or small scale purposes, they use UV light to kill again here the bacteria pathogens. Now, come to this point. What is microfiltration? Depends upon the size. We can differentiate these filtration systems. What happens that one? So we can say that microfiltration is up to 1 to 10 micrometers of particles we can able to remove. And then ultrafiltration 0.1 to 0.01 micrometers. And then if you're talking about nanofiltration in name itself, so we can say that 1 to 10 nanometers particles, even the very small particles, we can able to remove that one. And then the final thing is, which generally we use to our drinking water purposes, is our system. So in RO system, even they remove the salts also. That's why this is a problem now. Major problem we are facing in our household water filters also. So that should be according to the standards that ppm. That should be the 150. So that's first people you will have to check that how much you are getting that. TDS in ppm, that how much you are getting in your household water while you are drinking from your water filter. Now come to this point. So what other factors affects the removal of microplastics from the industrial effluents? We can say that while we are talking about industrial effluent treatment, the most important point is the cost of the technology. So we have given that one. So some modifications, even this process, even we have given some modifications. Sometimes those modifications also can affect their profits, and that increases that profit, that operational cost too. So that's why industries are more concerned about that, what they are doing and what they wanted to do. Here is the government initiatives, and if you're talking about that industrial parks, they are there. So government initiatives and government supports are most important. In particularly while we are talking about the startup stage and small and micro and small MSMEs, we can say that when companies they can't able to offer these advanced treatment plans. That I know some things what happens actually the behind that, but I shouldn't say on that open platform or what really happens in the industry. Oh, now India, and now what comes to this part, if we were talking about cost, in general, the usual cost of standard packaged drinking water is 0.5 to 2 rupees per liter. This includes raw water, electricity, chemicals, maintenance, labor, and next packaging expenses and everything. But we're talking about municipal water, industrial water treatment plants, is 1 to 50 paise per liter. Economics of scale, bulk processing, and reasons for this drop. So reverse osmosis, UV filtration technologies that purify water can somewhat increase the cost, but they also provide water at higher quality. Here, this is the most important point. So whether we have the technology, available technology, affordable technology, by using this such type of technologies or not, it is also one of the more concern while we're talking about industrial effluents. The source of water quality plant efficiency, additional local utility rates also factors in the final cost per liter. So water plants can keep treatment cost low, operation and waste minimization. Clean water will still be provided to consumers. So due to this cost per liter, if we're talking about that one, this is a problem that comes arises from here. So no industry wants to utilize, I can say that, and spend lakhs of crores of rupees and to remove the microplastics are 2 to 3%. We can say that most of the cases they can able to remove 95%. Yeah, you can say that from use whatever the method, but they can't. They are. I don't think so. People are can able to do these things too. That's why we can't able to stop 100% removal of the microplastics from the wastewater. Here, there is an estimated estimation how much you can able to remove the microplastics when we do some modifications to the conventional systems. So here we can say that one during this primary sedimentation, 41 to 61%, but you can say that one on that grid, we have that over the collected sludge, we can say that one 69 to 80% of the microplastics are still in sludge. So this is another problem here. How we are disposing that's collected sludge. This is a major problem. So can we say that? I don't think so. Microplastics are going to leave us how whatever you do, because we don't know how they are disposing the sludge. No one knows that one. Now come to the point here. Finally we can say that one. So we can able to remove that up to 98% from the effluent, 98% of the microplastics by using some modifications in that conventional treatment water treatment plants. Okay, but this purely that depends upon the social responsibility again, how the government should take care about that one, how uh, how they are treating the sludge disposable processes and all. Now, next point, come to the next point. So till now we have seen that one. There are the general process. We have understand how the process and how some modifications we can able to do to remove the microplastics from the wastewater industrial treatments. Now here there are some advancements are happening while we can say that when these methods there are under some are in pilot projects, some are ready to adopt to the treatment plants, and then some are at still under research level only. So we'll come across all these methods briefly, what exactly how they can help to remove microplastics from our effluents. Now come to the point. So what are the physical treatment method? So in this physical treatment method, we are not going to change any kind of property of the plastic, microplastics in terms of chemical and biologicals. We are simply using the shape and size. We can say most of the cases filter based. Yes, we can say that in most of the cases, filter based principles we apply here are sometimes adopted based sometimes yes adopted based things we apply principles we apply to remove microplastics from the effluents. Now, the first one we'll use that. So we're talking about filter. So there are two types of filters. One is the sand filter, another one is the disk filter. So we'll go through these two filters. So these two filters, we can say that when if you do the simple modifications, these two filters can easily fit into that industries, any industries. In large scale industries, I can say that one because not only the setup of these filters, these filters need a regular maintenance. So this maintenance cost is going to be increased. So where the micro and small industries can't able to afford this technology still. Now, what exactly the sand filter? A sand filter, we know that one is very basic principle. There are big tanks and they use different sizes of the sand particles. So they allow the effluent, the final effluent along through these layers, sand layers, and then that filter the microparticles get entrapped in this in between that the sand porous structures. Here we can able to remove 200, the greater size than 200 micrometer microcluster particles we can able to remove from here. Okay, so due to its, we can say that one, among all other methods, the sand filter, yes, this is a very good and feasible technology to remove microplastics and easily adoptable and easily set up, we can make setup into the small and micro scale industries also. So that depends upon the regulatory issues again. Now, again, what is the disk filter? So here we have seen that one, we are layered, we use the sand as a layer to filter that one. The same thing we use here, the disk based thing, they are the rotatory disk based and they sometimes they apply a vacuum also. And then this consists with the small pores, comparatively small pores, some cloth covered, we can say the less four size class, they covered steel mounted discs. And then when we allow the flow of fluid flows along with this chambers, we can say this. We can see that when there is a tubular chambers with along with this, what happens? This simple the minute particles here, that minute particles can entrap in this smaller pore size. The advantage and disadvantage of these things is, since it is cake forming, means that layer by layer it is forming. So regular maintenance and removing that cake and changing that parts, this is, we can say that a little bit complex, but more effective to remove microplastics from that to industrial effluents. So, and then next thing is right, adsorption process. So what is the adsorption? What is the adsorption process? Adsorption, while we're talking about adsorption process, is very simple. We always think about porous material. Here, what kind of porous materials are available for us? We can say that one. Here you can able to see the aerosols, sponges, metal organic frameworks, and then so for hydrophobic materials and multifunctional. So we can say that one, no doubt about it. These all materials are highly efficient and highly effective, but still they are under research only. So we can say that one. So what exactly we will go through one by one, what exactly they are. So what is MOF based observers? What exactly this MOF stands for metal organic frameworks. So we can say that one, what are the metal organic frameworks? We can say that are the nanoporous crystalline materials. This is the most important of this MOFs. So MOFs is not only for the, we can say that one, if anybody asks that what is the most advanced research is going on nowadays in terms of nanotechnology or metal sciences, metal oxide sciences, and whatever it may be, we can say energy, whatever field you take that one. So MOFs are the main on the top of this research field nowadays. So they have that much importance in our research, not only in research, they are that much efficient materials. So they made with then this made up of organic as well as metal complexes. They use both organic compounds and metal oxides, both the metal complexes, salts they use to prepare this metal oxide, MOFs, metal oxide, metal organic frameworks. But they have the porous crystalline structures. These are the most important. They are very stable structure. They have the definite crystalline properties and structures. It depends upon what kind of uh, precautions we are using, what kind of reactions we are doing, reaction conditions, and everything decides this one. You can see here. So that decides the shape and size of the porosity and overall structure of the TMOFs. Okay, so with this MOS generally they have the nanometer size nanometer that depend size of that depends upon the structure how we can control this size also. This is the greatest advantage in this MOFs value of synthesis. So they selective to do the selective synthetic procedures and selective process. Yes, even you can control the both size of the small these MOFs, small metal organic frameworks. So what's going to be happen? How these MOFs are going to use? How they collect the microplastics from the water? Generally, they since we are talking about metal organic frameworks, metal oxides as well as organic molecules, so they have five bonds. Even some sites means metal oxide sites, they can act as a even the overall side, they can act as a high electrostatic interaction centers. They are the charged centers, as well as we have the functional groups on organic molecules. And then, so overall strength, they can have the hydrophobic property. So while and even they can form the hydrogen bonding. So various that's the advantage of this MOFs. That's why these are more effective. So they can use all kinds of interactions, either charge based, even hydrophobic property based, even that function group based, the 5-5 interactions, even hydrogen bonding based, whatever the things are possible, all possible interactions they can have with the microplastics to absorb on these micro or nanoporous surfaces of the metal organism. Now, a second category of the porous materials, as we touched the micro MOFs are the solid and crystalline materials, so hydrogels, aerosols, sponge, and foam type of materials. These are not crystalline and they have very large portions and compared with the MOFs. Here, we can say that in hydrogel and aerosol and sponge, these type of materials, we can't able to control the size of the pore. We can't able to control the pore of the pore. And particularly if we are talking about hydrogel and aerosol, what is a hydrogel? The hydrogel is nothing but is the networked polymeric chains. We can say that when we can use the most of the cases again biodegradable polymers to make this hydrogel networks. So whenever they absorb water, before they absorb the water, they're very small in size. They looks like a powder only, but they can absorb hundreds of times of that weight compared to ratio the water. So whenever they absorb the water, what will happen? They start to swell. So whenever they swell, the pore size in the hydrogel is going to be increased. So there, they might have the similar, whatever we have seen in that in electrostatic interactions, 5-5 bonding, hydrophilic interaction, everything is possible. The hydrogel also, there they can easily entrap by absorbing the water along, the microparticles can entrap along with that hydrogel water, but there are a lot of advances are there in hydrogel. Even sometimes they are preparing that hydrogel based nowadays. People are working on hydrogel based filters, membrane filters also. They have the less swelling ratio, but they can act at the particular stage of swelling, the pore size are going to be stopped increasing. Now they start to act as a filters. For talking, if it comes to the aerosols are not we can say that like hydrogels, so they are fixed porous size and fixed materials. So they will, while making itself, aerosols are the porous materials, low density and porous materials. So they also have the same properties, depends upon the molecular structure. And now come to the hydrophobic and superhydrophobic materials. So what exactly the hydrophobic? You can say that one already we have discussed in the last previous session. The hydrophobicity will decide based on that droplet angle on the surface. So we can say that one is a superhydrophobic. If it is above 150, that's called superhydrophobic. But that angle in between 90 to 150, that's called hydrophobic. So what's the use of this hydrophobic or superhydrophobic materials? Since our plastics, microplastics are surrounded by the water molecules, so they try to attract to the easily onto the hydrophobic or superhydrophobic surfaces easily. So that's a basic principle we apply here to remove the microplastics from the water sources, aqueous-based solutions. So, and then what exactly this thing here? One example, they have done very good research. They have done that one. How you can see how they filter. The simple is the type of filter only. So in the first in the F picture, you can see that right corner, that schematic diagram. You can see that the initial stage, all microplastics, plastics are surrounded the surface of the water. And then whenever we add the hydrophobic solvents, we can say here they use, I think, hexane they use, right? Hexane they use, we can say the immiscible solvents. Immediately what happens that all microplastics are transferred to the surface of the layer of the hydrophobic surfaces layers. So here they use, we can say that an oil based oil, this is yeah, an oil film based method, instead of the same thing. If how we are going to modify our surfaces and the technology we are going to use, it depends upon that research. But still in research, we have to do a lot to adopt this method to the industrial applications. Now, come to this one. Same. This whatever we have discussed in earlier. This season, but in the things there you have used have hydrophobic and super hydrophobic surfaces by modifying the surfaces with something, surface functionalization or whatever it may be. But here, in oil film method, they use directly oil. This I can say this is a highly effective to recovery microplastics based on that hydrophilic and hydrophobic nature. But I can say this is the one of the worst to method to use for industrial applications because here a lot of concerns are there. Removing oil again, that cost will increase because it increases the stage level of stages of the effluent treatment, as well as the oil cost, as well as that sedimented particles and sludge. Oh, again, it causes to the, I can say that one, the secondary pollution. Instead of removing the microplastics, in my opinion, this is causing a secondary pollution causing through this method is more serious concern. So that's why, in my opinion, this is not that much right method for the large scale applications, but there is a one method also. That's why we are discussing. Now, this is another beautiful method. We can say that one this is more effective, and then yes, we can apply for industries because we can here they use a normal magnet, but we can use the electromagnets. They simply use that they prepared iron oxide nanoparticles. Where we're talking about 40 to 50 nanometer iron oxide nanoparticles. So these iron oxide nanoparticles are going to be adsorbed on surfaces of the microplastics. These microplastics are in microns. So they are going to adsorb on the surfaces. So when we apply that magnetic forces, they simply they can able to remove. So that's why in this particularly for polyethylene particles, they were able to achieve to remove 98.4% of the microplastics from the effluent. So here they apply 40 micron polyethylene as well as 200 micron polyethylenes. This is, I think, Korean-based university, Inha University. I think they have done this research in the lab. But is we can say here they simply said that what exactly principles are involving here. The population principle also is going to be applicable here. And then here we can see that they have given very nice results. You can see in the first picture. And the second picture, you can see the variation. The microplastics are clearly visible from picture one to the picture two. And at the same thing, they also have given this SEM EDS, energy dispersive spectroscopy based mapping. Here you can see the clearly how much iron nanoparticles on the microplastics. You can able to see that it is clearly able to absorb on that one microplastics. So yes, you can say that when this magnetic separation method for microplastics will work so far better. The reason is here the particles they can easily discard in safe way and control way. We can able to need much about that volumes of this iron oxide nanoparticles. So, but here one concern is there, that is the price of the iron oxide nanoparticles, the cost will be the major issue in this type of magnetic separation. Now come to the point. Next, right. So fourth flotation method. So we know that when this fourth flotation is very common, but I can say that it also is one of the easily adoptable and more effective for these industries by removing of the microplastics from the effluents. So we know that when the process is very old for centuries. In right-hand corners, you can see that two pictures where we already applied in household systems. So what exactly it is? It's nothing but they use the agitator, a stirrer, we can say in terms of in our lab terms, stirrer, they can use that one to make foam. So that microplastics are trapped in that bubbles of the foam, and then they are due to that the low density of the foam bubbles, so they reach to the surface of the water. They easily can able to remove that fourth flotation. So what exactly happens here? So, but again here already we have skimmed the skimming process during that primary treatment is the same. Yes, we can say that both treatments are similar, but here the only skimming, simple rotation of pumping air flow is not enough. That's the major problem here. What we need. So this purely we need to use some reagents. We need to use the reagents to improve the to foam and to stability of the foam. So there are a lot of things we need. A method of changing that hydrophobic in water. And that's we use generally methyl isobutyl carbinol and pine oil. This is a pine oil like this oils they use to improve the surface property or bubbling or foaming property, and that one. And next, they use that for stabilizers. They use that metal, even they use metal ions, all these things type of for some agents we need to add. This causes to the additional cost as well as may increase additional step to remove these agents from the water again. So this is also the concern. Another concern we have to take care about that one. But if they can able to do this step, if they can able to find a mechanism how they can able to adopt this same thing and immediately after primary system, maybe then that water can again we can pump into the primary system. So that may be the feasible when we talk about these things in terms of cost and implementation of this method to the industrial effluents. So, and then, yes, this is related to this. Yes, we can say that one. That this is a low cost and a continuous method source of promising cleaning water. The primary element we already spent this is nothing. So here we can able to remove the 96% of that one microplastics. So that's the much that's the greatness the effect of this fourth floating method. Yes, easily adaptable to the industrial effluent systems also with low cost, we can say that one. And then till now we have seen that when filter based, and we have seen that filter based. Wait. Yes, so we have seen adsorption, physical methods, adsorption and filter based, the flotation method, oil film, and magnetic separation. So among them, we can say that an oil film method is not effective. The remaining may be the adoptable, but a lot of the extensive research is needed. Now, come to the chemical methods. They are coagulation and flocculation, and then there's oxidation methods, photocatalytic. We can say that one advanced oxidation methods and solvent techniques. We can do these things. We'll discuss about few important chemical methods during these slides, coming slides. Right. So what are the chemical methods actually? Chemical treatments. In the physical treatment, we are not changing any chemical structure of the microplastics, but here we are going to do that thing. And chemical treatments are often important where microplastics cannot be removed from wastewater by physical and biological method. No doubt about it. The chemical methods are very effective in terms. So chemical treatment includes the application of different chemicals in series of reactions to promote the water purification process. In chemical treatment, microplastics present in water are forcefully removed by adding specifically targeted chemicals. So such methods convert harmful microplastics into less harmful chemicals. This is the one of the beauty of that chemical methods. When compared with to physical methods, see in the physical methods, since we are simply collecting the microplastics from the water, but what happens? This is another concern of physical methods. It's been able to remove microplastic from water 95 up to 96%. But what happens to that microplastic is trapped into these systems, physical systems in sludge. So which is again big question there. But we can say that one while you are talking about chemical methods, yes, we can able to remove completely the microplastics in terms of simply converting harmful microplastics into less harmful chemicals. This is another and most efficient point of the chemical methods. What are some examples of this treatment? Coagulation, percolation, electrochemical oxidation, photocatalytic degradation, ozonation, and solvent technologies are there. So we'll discuss a few of these technologies in coming slides. The first one is a coagulation and flocculation method. Again, this is also same we have seen in magnetic separation, as this is also similar, but here we use some coagulants. Those are maybe the metal salts and then polymers, some other biodegradable or even non-biodegradable polymers we use as coagulations. What are the stages there in this process? The first step is coagulation and rapid mixing. These two interacting with the microplastics are going to get interact with that coagulant molecules. So once they get that one, due to the hydrophobic some molecular interactions, what happens? They start to form agglomeration molecules. So that's called flocculation process. Once they get the agglomerated, the density is going to be increased. Slowly, they get sedimented bottom of the chamber. These are the stages are involved in coagulation and flocculation. We can say that one, this is the very common process even for drinking water purposes. So people they like to use this process for that coagulation, flocculation in water treatments or filtration or water purification process, whatever it is. This is but one to have was the key is another problem is it causes to the secondary pollution because the formation of sedimented things, everything. We are simple again. What we are doing that is removing the microplastics. To remove microplastics, a pollutant is already pollutant in water. We are adding another pollutant in terms of solid metal oxides and polymers and all these things. This is going to be another headache and burden of how safe we are able to dispose of this sedimented things. So what exactly we use here? This one, we can say the most used coagulants are aluminum sulfates and ferric sulfates and ferric chloride. And even sometimes they use to remove the polystyrene. The people want achieve ferric chloride to remove the microplastics is roughly 78%. And then combining, this is the one more thing, another point, combining two different types of coagulant processes like alum and polyacrylamides. Polyacrylamides, you can say they are biodegradable, no need to worry about the polyacrylamides. Can effectively able to remove that low density polyethylene high-density polyethylene and polypropylene from synthetic storm of water, 92 to 80, 96% we can say that one. So this, yes, no doubt about it. Again, these coagulants are very effective, but the only concern is what happens later. And then the range of coagulants and and then this options such yeast, even sometimes they use that biological options such as yeast and starch for they're using for the alternative to the polyacrylamide and aluminum chlorides. So this is also now the modifications are happening and updates in the research is happening nowadays. So if it is really can able to replace these salts and acrylamides with starch and biological options, that's we can say that and that's very good. And then now, so they said that the combination of the coagulation and circulation are different various types of materials, so that coming is more effective to remove these microplastics from the industrial wastewater. And as we discussed earlier, the major drawback of this type of things is a sludge, the formation sludge disposal. Now come to the advanced oxidation procedures. There are two kinds of advanced oxidation procedures. We can say that one is simple ozonation. Everyone aware about this technique. Another one is the photocatalytic oxidation. These two called advanced oxidation. What happens when we use that ozone, ozone gases to these things? Excuse me for a moment. Okay. So MP remove microplastics removed by ozone treatment is better than filtration systems. That's no doubt about it. How they can how that it happens. So ozone is green agent, the strong oxidation potential 2.07 eV. This is the most important point here, and is used as a chemical reagent in water, wastewater treatment, and disinfection test. Almost all. So we can say that when the ozone treatment is one of the most efficient and acceptable treatment filtration process. How it's going to be remove our microplastics. This is the most important. We need to understand that one, what exactly happens. So you can see that one, whenever the ozone is involved, so you will get generally a radical ions. These are radicals, free radicals. We can say that one. Sometimes free radicals and ions, they combine, they both can form also radical ions. So it's possible to form that one. So these radicals, these free radicals, when interact with the microplastics, in microplastics, what we have that one, we have the chemical structures, so they can easily interact with these polymer chains and they enter into these radicals into, they can easily enter into these bonds. Those bonds, they can easily cleave here. You can see this one. You can see they simply react by oxidizing and getting interact with those bonds. So they get involved and enter into this polymeric chains. Then they break down the polymeric chains, and then they simply they come into the small molecules. So this is a most important point. Yes. So this is we can say that among the all methods, removing microplastics using oxidation process is I can say 100% efficient method. So removing this small, you can say not much harmful compounds are there here, but those also can able to remove using the photocatalytic oxidation method. So even everything we can make a simple 100% degradation process. Now, so what happens this one? So ozonation is investigated 89.9% of the remaining microplastics was eliminated by the ozonation process. So the elimination of the microplastics may include high operational cost. Here, that's true. So whatever the advanced type of a highly efficient methods we wanted to use, the always cost is the more concern. The major drawback of the ozonization process is insufficient ozone process. Ozonation can causes to the intermediary compounds. Those are highly risk to the public. So it means if you can't able to do the proper ozonization, that's going to be a more risky than microplastics to raise. Now come to the another method that is called photocatalysis. This is also considered as a advanced oxidation method only. What exactly is a photocatalysis? The principle is the same, either in ozonization or in photocatalysis. The principle is the same. Simply, they both form free radical in the solution. But the free radical mechanism is entirely different. As we know, ozone structure itself, this is a highly stable chemical. That's why they can, whenever they interact with the water, they can easily form the radicals into the solution. But if you come to this photocatalysis process, here we use semiconductors. What does mean semiconductors? Many of you know more better about these semiconductors, but I would like to little brief the whoever maybe biology people, biology background people. I would like to give little brief on this semiconductor. The semiconductor is nothing but metal oxides. We can say that when we know that when metal iron is the conductor. If you come to the iron oxide is a semiconductor. We can say this is in the thumbnail. You can say most of the metal oxides are the semiconductors. In terms means they don't to process the electricity easily because they have a gap. This is, you can see that in the picture, you have a gap in between these two to transfer electron easily from lower ground states to the upper state. So here you can see the valence bond and conduction band. No need to worry about that one. Is valence bond is nothing but in terms of molecular orbital theory, we can say that one highest occupied molecular orbital HOMO and lowest unoccupied molecular orbital. These things we can get one these things, but don't confuse both concepts are entirely different. Both are not same. Okay, but you can say that one. So there is a gap in that metal oxides. So that's why an electron not easily jump from ground state to the upper state. So when you're able to give that equal energy, that band equal to the band gap, and that electron simply can reach to the upper. That is called excitation, which we are already using the principle in the UV spectroscopy. There, and then there is a vacant site in that conduction band that is called hole. Nothing. So don't worry. For physical physics, the purpose of the calculations, they use the word hole, but actually that is a vacant. And then if you come to the conduction band, there is an electron extra. So that is called an that causes to the reduction reactions, and then here again that hole has that the space ready to accept an electron. There the oxidations will happen. This is the same simple thing. This happens in the, whenever they interact with these reactions whenever they interact with the solutions, so when they absorb the UV light, it will happen. Again, I can say that one nowadays, this photocatalysis research is one of the promising and prominent research area. And yes, it can able to get that results are very good. We can able to get in terms of energy and then water purification and even in biology to kill the bacteria also. So it's everywhere you can research is going on. But the main point is the drawback is again I am talking about the preparation methods and expensive, the preparation of nanomaterials, consistency of the procedures, everything. This is a little bit comparatively expensive when that ozonation process. Now here we can able to see this in the right corner image, the equation. So you can able to see that whenever it is absorbed from the electrons, you can able to oxide radicals. You will form the oxide again whenever interact with the water. You can create these ones superoxide radicals. Here superoxide radicals will form. So these radicals are going to interact with microplastics. Here you can see the sequence of the reactions, how is these radicals are going to change the structure of the various microplastics. So finally what happened, they degraded into a similar type of these things, but this mechanism is entirely different. Here the free radical mechanism will approach, so they can break any bond that's more conveniently. It is a most effective when compared with the ozonization and radical systems. So these molecules does easily get and then cleavage and this symbol that can cause to the cleavage and branching and cross-linking on various reactions will happen in that long process. Now come to the another. So now here we have seen that when the chemical processes are completed, now come to the sorry, it's already I will finish with 5 minutes, within 5 minutes. Sorry, and I have also work another work. Okay, so okay. Now complete to the, we all last process we came to the biological filter biometric yes, it's a biofiltration method. How we can able to remove here use is very simple filtration process, but they use biochar. What is a biochar? The biochar is nothing but we can say that one is a combustion process under controlled environment conditions. If you use any feedstock or plant wastage at 400 degrees Celsius with a minimum amount of oxygen and 400 degrees Celsius at controlled environment, you get brown or carbon type of compound that's called biochar. Even in nowadays, even in agriculture purpose also, this is very good for lands, agriculture lands also, because it retains because of its porosity. You can see this. See the beauty of this thing. It depends upon the which type of feedstock you are going to use to prepare the biochar. There are wide variety of the for sizes, shapes, and all you can able to attain that one. So those can, and when you combine with the sand and this biochar and the filter can come can trap the all kinds of microplastics, including fiber type of microplastics also are possible to filter using these biofilters and biochar filters. So here we can able to use remove that 80% of the or even 95. It's possible. How much for size and which feedstock? This is a trial and error. Once it's stabilize, able to stabilize the process, there you can able to remove 100% of the macroplastic. That's one of we can say that the most effective method. But I can say that one this is little bit slow process as well as again it may cause us to the if you don't dispose properly, it may cause us to the secondary pollution of the environment. So this is a major concern while we are talking about biofilters and biochars. Now, the last stage we came to the biodegradation. What is exactly the biodegradation? It's nothing but as photodegradation. Here also same thing. These or microbes like bacteria, algae, fungi, they are going to break down these microplastics into small molecules by using the ATP and TCA cycle. I'm not much aware, or sorry about that one. I'm not much familiar with these biological cycles, but I can able to tell briefly. So this is the reason, but it is a very slow process. So in terms of that one, it still these are not we don't have that confident results how affect all this, because we can say that one, since we are using here this photocatalysis and ozonization, either they have the high energetic conditions, so the degradation process will become faster. But how faster, how effective, I am sorry about that one. I'm not clear about this biodegradation process. Now come to the membrane bioreactor. What is this? It's nothing but, so what we are doing here, we are simply doing here biodegradation process. After that biodegradation process, so we can say that this is called membrane filtration tank. Here what we do, that one, we simply use that membranes where we can able to filter these microbes, we can say that ultra nanofilters, we can use that one, which we are using nowadays in our household filters. So that's why they are a little bit expensive. So where they can able to, you can get ultra pure water. Depends upon the pore size, which type of this one filter you are using to filter this one. What kind of these things. So this is very simple. Here you can able to remove 99% of 99% of the 99% of the microplastics you can able to remove. But there are the major challenges, this membrane fouling and mixed findings. They found that one, and the scale up the cost. This is the another thing. While we are talking about that of membranes, here we can easily do this, you can able to do the first stage, but the major problem is it comes from the filters. The filters are very expensive, and you might know, everybody, every one of you, while you are changing your filters in your home filters, so if you think about that large scale, how expensive it is. So, but still we need to do a lot of extensive research on this, need to do research on this advanced techniques to improve their adaptability, and then cost effective methods. And then the major concern is, all most of the cases we have seen that the sludge disposal process. So we need to, if anybody interested on this, there are a lot of research scopes in the water purification process, particularly like India, like overpopulated and then developing country, yes, need low cost and effective technologies. And thank you. Now it's already too late that I will leave us 7:20.
So thank you, Dr. A.B.V. Kiran Kumar, for your great contribution for this FDP. If it is possible, if you unmute a video, we will take a screenshot.
One more. Okay. One moment. Let me copy somebody last. Could I don't have time? So if anybody have a doubts, please drop me in my email and I will reply surely to you.
Yeah, now
So
I'm
my
cordially
question is
inviting
this.
Miss.
Yeah, any questions, please drop me an email. I will reply to you. Last time also, I think I have given questions, since it's already 7:20. I have to leave for another work. Okay. Can I leave now, Professor Saraswati?
Yeah.
Yes,
Wait,
please.
sir. Let us give vote of thanks. Now
Okay.
I am cordially inviting Miss Pranaya to extend her vote of thanks on behalf of organizing committee.
Thank you, madam. I sincerely thanks Dr. A.B.V. Kiran Kumar sir for his valuable section on process of intensification for the removal of microplastics in industrial effluent. Your industrial viewpoint gave us new directions. Thanks also to the participant for the engaging questions, ma'am. Thank you, ma'am.
Thank you. Yeah, thank you. Now you can. Dr. Siva Prasad, are you ready?
Yes, ma'am. Hello.
So you can.
Yeah, is it
You.
audible now?
No, it is not shared. You are, yeah, it's
Yeah,
okay.
is audible now? I will share.
Yeah. You can get ready with sharing screen. Sorry.
Okay.
So let us invite by our one of senior most faculty, Dr. T. Naveen Reddy. Sir, it's pleasure to invite Dr. T. Naveen Reddy to introduce Dr. V. Siva Prasad Reddy.
Good evening, everyone. Hope you people hear me. Am I audible?
Yeah, audible, sir. Audible.
Um, okay. Good evening, everyone. Welcome to the session 12 of our FDP program. I'm very happy to introduce Dr. V. Siva Prasad Reddy. He is now presently working with Sri Vasavi Adhesive Tapes Limited, Bangalore, where he is leading the instrumental in the development in commercialization of innovative products such as waterproof wood adhesive, flame retardant adhesives for Indian railways and advanced construction chemicals, epoxy resin systems, medical grade pressure sensitive adhesives, and eco-friendly water-based paints. He has been having a 7 years of industrial experience, and he has completed his MSc and PhD degrees in polymer science and chemistry. And his basic strength was in industrials and coatings. I will hand over the session to Siva Prasad Reddy. Okay, now the session is yours, sir.
Yeah, thank you, sir. Thank you. Yeah, is audible now? Okay, is audible?
Yeah, audible,
Yes.
audible.
Yes, yes. Okay. Yes, yes. Yeah. Respected Chairman Pratap Reddy sir, respected Principal Srinivas Reddy sir, respected Coordinator Dr. Saraswati Garu, Associate Professor in Chemistry, and respected resource persons and respected participants, a very good evening to one and all. As in previous sessions, we learn clear understanding of microplastics as emerging contaminants and modern techniques for sampling, monitoring, and analyzing microplastics and the environmental and health implications of microplastic pollution. And familiar with international research, international trend research in polymer therapeutic also. And this present session also contribute to sustainable environmental solutions through green catalysis for accelerate degradation of microplastics under ambient conditions. Why green catalysis is needed in microplastic degradation? Traditional catalytic methods can have significant environmental impacts, making green catalysis a more sustainable and alternate. So green catalysis minimize the toxic chemicals and reduce the risk of secondary pollution and improved degradation rates. Yeah. See, now the planet was drowning in every year million tons of plastics, microplastics, as we are aware. We have been found in distilled water also. This is not a science fiction. It is a projection based on current trends, even every day. And equivalent to one of garbage full of plastic enter into oceans and now being found in water and table salt even inside of human body also. As we know, the microplastics are less in particle size, 5 millimeters in size, smaller than like a sesame seed. And microplastics was everywhere in oceans, rivers, soil, and even in our air breath also. This is not just an environmental crisis, it is a health crisis, and that's why we need solutions that are innovative, sustainable and effective under everyday conditions. Yeah. Can the plastics around us completely degrade in our lifetime? No. The reality is sobering. Most plastics take 500 years to degrade naturally. That means the water bottle you drank from this morning will outlive not only us, but several future generations. This is why scientists are exploring green catalysis, a way to accelerate plastic breakdown under everyday conditions.
Dr. Siva Prasad, sorry for the interruption. Share the screen, full screen. It is off in the system. Okay, if you don't mind.
This, okay.
Yeah, you can make it on the top at the into mark, near the into mark, you can make it full.
Get full.
No, on the top there is a into mark.
Yeah, now it's
No. You can open. No. Just close it once again, you can open.
Okay. Is it,
Double click, give double click.
no, it's not.
No, close. There is a into mark, na? So next there is one. You can click on that. At the top, right side.
The box in the right corner, the box, small box on the right corner. If you go to the right corner.
There is like a box.
Now it's okay?
No. Right corner. Now it is okay.
Okay.
No, again, it is coming a presentation.
Yeah.
No, yeah, there is
close
a
the-
into. You are closing, na? No.
No. Beside that.
Near the closing, there is a box. You can open. You can open again. You can open.
Can I leave and again connect? Hello.
No need, sir. No need, sir.
You can.
1 minute.
You can open PowerPoint now. There is a PowerPoint, na? You can. So here box is there, na? There into mark is there. On the top.
Maximize button.
You can maximize the.
So click on the maximize button on the right side at the top.
Right side, there is a cross mark, into mark to close. Before that, there is a box on the top.
Sir, Windows plus up mark, sir. In keyboard, Windows and up mark, upside arrow. In keyboard,
So then, if
press
you do
in
like
Windows and up arrow.
Then near to negative button.
Mm-hmm.
There's the center button.
there next. Yeah. You are closing the next. There is a box. You can click on that.
Already it is closed.
No, can I close and leave and can I connect again? 1 minute.
Aha. So you
Sir,
can
there is a
go.
square box just beside that into, sir. If you click that, it will be maximized.
Sir, on the top bar, the button between minus and cross. On the very top.
On the top of that slide, sir, whatever this PPT you're opening, on the top bar, on the top, sir, there is a cross option. Just behind that, there is a square box. To your right side.
Maybe there's a problem on his screen, ma. So let him continue because it is visible only. Na? Let him continue. Hello. Hello.
Sir,
Now
now it
it's
is okay, sir. Go ahead, sir, please. Now it is okay. Hello, sir. Sir, it is clear now. Please go ahead, sir.
Maybe your voice is not audible. Check the microphone. Siva Prasad.
Okay.
Okay.
Yeah.
Yeah. You
Yeah.
can
Understand
continue.
the microplastic crisis and explore green catalysis principles, eco-friendly, energy efficient methods for plastic degradation, review breakthrough research and case studies, interactive brainstorming of solutions, reimagine a sustainable plastic-free future. So what are microplastics? We are now aware about microplastics are defined as a plastic fragments smaller than 5 mm. Some are intentionally manufactured like microbeads in cosmetics, while others come from the breakdown of larger plastics like bags and bottles. Source of microplastics. From toothpaste to t-shirts to tires, microplastics originate from everyday products. Even washing synthetic clothes releases millions of microfibers into water system. What is the environmental impact from microplastics? Contaminate every corner of the environment, oceans, rivers, even agriculture, soil, fish and marine animals ingest them, and the particles climb up the food chain. And human health concerns, studies have now detected microplastics in human blood and even in the placenta. Their small size allows them to cross biological barriers, raising concerns about long-term health risks. So global statistics, on average, each of us unknowingly consume about 5 grams of microplastics every week, roughly the size of credit card. So why do plastics don't go away? So plastics were designed for durability, not degradability. A bottle used for 10 minutes can persist in the environment for nearly half a millennium. So the traditional degradation methods, current methods like landfilling, burning, and recycling are not enough. Recycling so can only be done a few times before plastic quality drops, while incineration creates toxic emissions. So the real world example, river pollution in India, major rivers like the Ganga and Yamuna are heavily polluted with microplastics. Most samples revealed polyethylene terephthalate and polyethylene, the same materials were used in bottles and packaging. So microplastics are now found in the most remote places, even in Arctic ice and Himalayas, proving how unstoppable they have become. So why green catalysis is needed. Microplastics are everywhere, environment, food, humans. So traditional methods are very poor, so ineffective. So a new green and accelerated solution is the only way forward. So we have seen how serious and widespread the microplastic crisis is. Now the question becomes, how do we solve it sustainably? That brings us to green catalysis is the way to sustainable. So from problem towards solution, the microplastic crisis has reached alarming levels, threatening ecosystems, human health and future sustainability. And traditional degradation is slow, so leaving plastics to persist for centuries. So we must shift our approach from passive observation of pollution to active science to driven interventions. One of the most promising answer is green catalyst, a strategy to speed up plastic breakdown under ambient conditions. So what is green catalysis? Green catalysis is the process of using a substance to speed up chemical reactions without being consumed in the process. And green catalysis applies the principles in an eco-friendly way, ensuring that the process itself does not add further any environmental burden. What is the importance of green catalysis? Use of non-toxic and sustainable catalyst functioning under mild ambient conditions, even in room temperature. Generation of minimal of no hazardous with byproducts. In the context of plastics, green catalysis means accelerate the breakdown of rigid polymers, which is not highly covalent bond polymers, into simpler, safer molecules that can re-enter natural cycles. This approach aligns with the larger vision of green chemistry and the circular economy. Why catalysis matters? Particles are highly durable, designed to resist natural degradation. So traditional degradations are very poor. So it takes decades to centuries. So leads to fragmentation to smaller microplastics and nanoplastics, which persist and spread further. Catalytic, so we are using catalytic matter in microplastic degradation to substance that accelerate chemical reactions to break down microplastic into smaller. So these catalysts can be categorized into several types, like photocatalyst, that is materials like titanium dioxide, zinc oxide, and graphite, carbon nitride, and that generate reactive oxygen species when activated by light, breaking down microplastic polymer chains. And enzyme catalytics also, we are using natural enzymes such as lipase that provide substrate selectivity and can degrade specific types of microplastics. And also with the using of metal ions like ferrous that participate in penton chemistry, generating hydroxyl radicals to degrade microplastics. And the nanoparticles also like that ferrous oxide that can catalyze microplastic degradation and be converted to for subsequent use. And metal organic frameworks, porous materials also composed to metal ions are clusters linked to organic ligands which can absorb and catalyze microplastic degradation. And hybrid catalyst also we are using, combining different catalytic mechanisms such as photocatalyst and enzymatic catalyst to enhance degradation of efficiency. So catalytic degradation speed up the breakdown process dramatically and work under ambient temperatures, energy efficient conditions by making plastic degradation faster, safer, and more controlled. Catalysis addresses both environmental persistence and waste management challenges. Yes, yeah. For degradation, we are using principles of green chemistry principles we are applied. Yeah, green chemistry principles aim to reduce the environmental impact of chemical process when applied microplastic degradation. These principles are included. One is prevention, designing processes to prevent microplastic formation or minimize their release, and atom economy, maximizing the efficiency of catalytic reactions to minimize waste, and less hazardous chemical synthesis, and designing safer chemicals, safer solvents, and using the auxiliaries, design for energy efficiency, use of renewable feedbacks, reduce derivatives, catalysts using for reactions to enhance efficiency and reduce waste. So by following these principles, green catalyst ensures not just faster degradation, but sustainable and responsible degradation. Mechanism of catalytic degradation. The mechanism of catalytic degradation of microplastics involves the breakdown polymer chains into smaller fragments or monomers. Following this absorption, microplastics absorbed into the catalyst surface and activate the catalyst activated by light, heat, or other energy sources. And reactive species generation. The activated catalyst generates reactive species such as hydroxyl radicals and superoxides. Polymer chain scission. The react species attack the polymer chains, leading to chain scission and fragmentation. And the fragmented polymer chains are further degraded into smaller molecules such as monomers or oligomers. So the mechanism underpins all green catalysis strategies, whether enzyme driven, light driven, or nano assisted. So type of catalyst we are using for accelerating of plastic degradation. To tackle the complexity of plastic degradation, scientists have developed several categories of green catalyst, each with unique strength. Catalyst, biocatalyst, naturally occurring protein like PETase and cutinase for highly specific and biodegradable. And the second one is photocatalyst, activated by sunlight or UV light to generate reactive species that attack plastic bonds. And electrocatalyst, using controlled electrical energy to drive degradation reactions, especially for promising of wastewater treatment. Yeah, nanocatalyst. Nanocatalyst also is used for accelerate to microplastic degradation. That engineered nanoparticles with very high surface area, it improve contact with the plastic particles and accelerate breakdown. And hybrid catalysts combine two or more catalyst approaches, so it will supposed to enzyme and nanoparticle systems for enhanced stability and efficiency. So no single catalyst is a magic bullet. Instead of one catalyst per hybrid catalyst, these categories respond and approaches adaptable to different environments. Suppose another different environments, we can scale up hybrid catalysts. Enzyme-based catalysts. Enzyme-based catalyst utilizes biological enzymes to break down to smaller particles. These enzymes, often derived from microorganisms, can specially target certain types of plastics. Lipases break down ester bonds. Esterases hydrolyze ester bonds in various plastics. Cutinase degrade cutin, a polyester found in plant cuticles, and more synthetic polyesters. And the mechanism is that in the enzyme based. So enzymes bind to the microplastic surface, and enzymes catalyze the hydrolysis of polymer bonds. And so microplastics break down into smaller fragments on monomers. So this is best advantage of this enzyme catalyst. Enzymes can target specific plastic types, and also enzymatic degradation often occurs under mild temperatures and pH conditions also. Even low pH below 7, environmentally friendly. Enzymatic degradation is very environmental friendly catalyst. Is a more sustainable approach compared to chemical bonds. So the challenges in that catalyst, limited activity on highly crystalline plastics, so slow rates compared to the chemical catalyst, need for optimization for industrial scale up. We can't scale up with these enzymatic applications. Photocatalysis for microplastic degradation using light driven catalyst, mainly semiconductors, to generate reactive species that fragment and oxidize plastics under ambient conditions. The key mechanism is titanium dioxide, zinc oxide, and graphene absorbs ultraviolet visible light and excited to electrons, holes generate reactive oxygen species like hydroxide, oxygen, and hydrogen peroxides. So the polymer attacks on chains leading to oxidation, scission, and mineralization, carbon dioxide and water, smaller biodegradable molecules. So the polymer degrade with the smaller fragments. For example, titanium dioxide nanoparticles widely studied strong oxidative power under ultraviolet. A graphene carbon nitride visible light active promising for real sunlight use. The advantage with photo catalyst was use abundant solar energy. We can use solar energy. So operates under ambient temperatures and pressure, can be integrated into water treatment systems. Challenge is need for recovery of photocatalyst particles and limited penetration of UV and risk of incomplete degradation. So future direction was development of visible light active catalyst, hybrid photocatalysis combining with enzymes or phenton-like reactions, photocatalyst, embolization on supports for reusability. Phenton catalysis is a process that uses iron ions to catalyze the decomposition of hydrogen peroxide, generating highly reactive catalysts, hydroxyl radicals. These radicals can oxidize and degrade organic pollutants, making phenton catalysis a useful technique. Application with using this catalyst, we can use in wastewater treatment, degradation of organic pollutants in industrial wastewater, and soil remediation of contaminated soil and groundwater, and for organic synthesis for complex organic compounds, we can use phenton catalysis. So what is the key component in this catalysis? Iron ions, that Fe2 plus to Fe3 plus ions catalysis for the decomposition of hydrogen peroxide, and hydrogen peroxides oxidizing agent that generates hydroxyl radicals, and hydroxyl radicals OH minus ions highly reactive species that oxidize organic pollutants. So the advantage of this phenton catalysis, the degradation effectively the degradation will start. Phenton catalysts can effectively degrade a wide range of organic pollutants. Challenges in this catalysis was requires acidic pH, typically 3 in acid media for maximum efficiency, sludge generation due to excess iron ions, and risk of forming partial oxidation with byproducts. Phenton and photopenton catalysis offer a powerful, low-cost oxidative pathway for microplastic degradation, especially when integrated with solar energy and green chemistry principles. Electrolysis catalysis using electrically driven reactions to generate reactive species and accelerate the oxidative degradation of microplastics in water systems. Mechanism also applying electrical potential across electrodes in aqueous medium to generate hydroxyl radicals and hydrogen peroxides and ozone at the electrode surfaces. For example, boron doped diamond electrodes highly effective in generating hydroxyl ions. Carbon based electrodes, graphite, nowadays using graphene modified, cost effective for alternatives. Electropenton process combines electrolysis with penton chemistry for enhanced efficiency. So advantage of this electrocatalysis operates under ambient conditions. Usually no need for external chemicals beyond water and dissolved oxygen, can be powered by renewable electricity, solar and wind energy, and easily integrated into wastewater treatment systems. The challenges was in this system, energy intensity if not optimized is a problem, and also electrode fouling due to deposition of degraded products, and scaling up to large water treatment facilities requires durable, low-cost electrodes. So electrocatalysis provides a clean, electricity-driven solution to microplastic degradation with strong potential when aligned with renewable energy and hybrid catalytic system. So here one more accelerate for microplastic metal organic frameworks in catalysis. So MFOs are porous materials composed of metal ions or clusters linked to organic lesions. In the context of microplastic degradation, MFS can be used as a absorbents. MFS can absorb microplastics, concentrating them and facilitating degradation. And catalysts, MFS can catalyze chemical reactions that break down microplastics, and MFOs can harness light energy to drive in photocatalytic reactions that degrade microplastics. Advantage in that high surface area, you can concentrate at a high surface area and have high allowing for efficient absorption and catalysis. And sustainable stability is also more. MFOs can be designed to be stable under various conditions, including water and light exposure. The mechanism was metal organic frames can absorb microplastic through interactions between surface and the microplastics. Advantage in this system, ultra high surface area up to 7,000 meters square per gram, and tailorable structure, specific targeting of different plastics. We can tailor-made structure, specific target, and possibility of multifunctional MFOs, enzymes carriers plus photocatalyst, and stable under ambient temperature. Challenges is high synthesis cost, and for large scale use, potential leaching of metal ions into the environments, need for stability improvements under real wastewater conditions. MFS are next generation catalytic platforms with the versatility to accelerate microplastic degradation through absorption, catalysis, and hybrid approaches. Hybrid catalytic systems, it's combine multiple catalytic strategies, suppose photocatalysis, biocatalysis, electrocatalysis, penton, and metal or MFOs to overcome individual limitations and achieve synergetic microplastic degradation. So when we are mixing hybrid it, so the photo with biocatalysis, that light activated catalyst generates ROS, that weak polymer bonds, so that the enzymes then complete biodegradation. And when hybrid with electrocatalysis and penton systems, electricity drives continuous Fe2 plus generation So it will sustain the hydroxyl production for effective breakdown. And the MFO plus with enzyme hybrid system, MFOs protect and stabilize enzymes while also catalyzing oxidation reactions. With the hybrid photo plus electrolysis catalysis, light plus electrical potential generate higher ROS, so flux compared to either method alone. For example, PETase plus titanium nanocomposite, it enhanced PET degradation via enzyme photocatalyst, and supposed to electrophotopentan process faster and more complete plastic mineralization. MFO and immobilized enzymes increased enzyme stability, recyclability, and higher degradation efficiency. Advantage was with the hybrid system, one catalyst compensates for another weakness. So faster degradation under ambient conditions. So sustainability is solar plus renewable electricity we can drive on. So still works on different plastics. It will works different. Suppose any hybrid plastics also it works in real world waters. Challenges was complexity of suppose compatibility, that complexity of designing and optimizing multi-catalyst system, and potential cost escalation due to multiple materials, need for scaling strategies without compromising eco safety. So hybrid catalytic system represent the future of green catalysis, enabling faster, more efficient and sustainable solution to the microplastic crisis. Real world applications. So what is the reality in applications is a pilot studies where green catalysis has been applied for plastic degradation under ambient conditions, for photocatalytic degradation of PET using titanium dioxide, pilot test in lab scale water reactors, and the enzymatic degradation with PETase and metase engineered enzymes applied to post-consumer plastic waste. So it demonstrated that near complete PET breakdown into monomers unusable for recycling. Yeah, some more examples with the electron penton treatment of microplastics in wastewater, that effective in reducing particle size and oxidizing in polyethylene, and highlighted potential integration into municipal treatment plant water treatment plants, and the MFO plus enzyme hybrid in bioreactors. It improved enzyme stability and recyclability, and accelerate plastic depolymerization under mild conditions. Future directions in green catalysis, exploring the next generation innovations that can make green catalysis more effective, scalable, and globally impactful for microplastic degradation, and synthetic biology and protein and engineering, in designing super enzymes with higher activity, stability, and broader substrate range, and smart photocatalyst, visible light active materials turned for real sunlight, for self-cleaning catalyst also with the anti-fouling properties, and integrated catalytic membranes. So supposed to filters that both capture and degrade microplastics simultaneously, and hybrid reactors for combining photocatalysts, electrocatalysts, and penton systems in modular units. Conclusion, microplastics are globally crisis, threatening ecosystems, human health, and the future of oceans. Green catalysis provides offering sustainable, eco-friendly pathways for accelerated plastic degradation under ambient conditions. Multiple catalytic strategies exist: biocatalyst, photocatalyst, pentan or photopentan, electrolysis, electrocatalysis, and MFOs and hybrids. Synergy is the future. Hybrid systems combining biological, chemical, and physical catalysis show the most promise. From lab to real world, case studies demonstrate feasibility, but scaling and eco safety are the next big steps. Nature took millions of years to create balance. With the green catalysis, science can help restore it in decades, not centuries. Final call to action to address this green catalyst for microplastic degradation. To address the pressing issue of microplastic pollution, we must implement green catalyst solutions, develop efficient catalyst, suppose design and synthesize catalyst that can efficiently degrade microplastics, and we have to scale up green catalyst process for practical applications. We have to collaborate to cross disciplines, foster collaborations among researchers, policymakers, and industries to develop sustainable solutions. And we have to promote sustainable practices, reduce the plastic use, minimize single-use plastics, and promote reusable alternatives, and improve waste management, enhance waste collection, sorting, and recycling infrastructure. And we have to raise the awareness in society, educate the public about microplastic pollution and the importance of sustainable practices. And we have to support research and development, fund research, providing funding for research on green catalysis and microplastic degradation. We have to encourage innovations, support the development of new technologies and materials that can help mitigate microplastic pollution. And we have to take collective action, global cooperation, encourage international cooperations to address the global issue of microplastic pollutions. And we have to engage local communities in efforts to reduce plastic waste and promote sustainable practices. And we have to change the policies, advocate for policy changes that support the development and implementation of green catalysis solution. Thank you one and all for your kind attention. Sorry for some disturbance. Thank you, sir.
Yeah, thank you, Dr. Siva Prasad Reddy. Let us invite Miss Sailaja to give vote of thanks for this session.
Hello, good evening all. Our sincere gratitude to Dr. V. Siva Prasad, R&D Manager, Vasavi Private Limited, for his inspiring lecture on green catalysis for microplastic degradation under ambient conditions. Your applied research for focus has motivated us all. Thanks to everyone for their enthusiastic participation. Thank you.
So, Dr. Siva Prasad, you may stop sharing.
Okay.
Dr. Vishwanath, sir?
Yes, ma'am. Yes, ma'am.
Let us start our next session.
Yes, ma'am. Yes, ma'am.
Okay?
Yeah, yes, ma'am. It's okay. Fine.
Yeah.
Yeah.
So, it's my pleasure to invite Miss Manjusri to introduce Dr. Buddola Vishwanath.
Good evening, sir. Good evening, ma'am. Am I audible to everyone?
Yes, ma'am.
Yeah, audible. Good.
Okay. Thank you, Saraswati Madam, for giving this wonderful opportunity. And Dr. Buddola Vishwanath, founder and director, Dr. Buddola's Institute of Life Sciences, Tirupati. Ladies and gentlemen, distinguished guests and enthusiastic participants, it's my pleasure to introduce to you our speaker for both session 13 of this ATAL Faculty Development Program on Microplastics as Emerging Pollutants, Analytical and Monitoring Perspectives. Please join me in welcoming an eminent researcher in environmental microbiology, Dr. Buddola Vishwanath, founder and director of Dr. Buddola's Institute of Life Sciences, Tirupati. Dr. Vishwanath is a scientist whose career beautifully combines academic excellence with social responsibility. With a PhD in microbiology from Sri Krishnadevaya University, he has dedicated his research to exploring how enzymes, fungi, and microbial systems can detoxify the environment, addressing pollutants ranging from xenobiotics to the pressing problem of microplastics. His pioneering work on Sternium Austria and its lacase enzyme has opened promising pathways for eco-friendly bioremediation. With over 50 publications, 12 books, 4,000 citations, and H-index of 30, Dr. Vishwanath has made significant contributions to the field of environmental research. He currently serves as chairperson of the Institutional Animal Ethics Committee and continues to advance research in areas such as microbial imaging, chromium detoxification, wastewater treatment technologies, and probiotic-based cleaning products as sustainable alternatives for environmental cleanliness. Ladies and gentlemen, let us warmly welcome Dr. Buddola Vishwanath. Welcome, sir.
Thank you, ma'am. Thank you very much. Yeah. Respected colleagues and dear participants, a warm welcome to this final session of our FDP on microplastics as emerging pollutants, analytical and monitoring perspectives. Yes, we conclude this FDP not with closure, but with a gateway to the future of chemistry and life sciences. Today's lecture invites us to stand at the intersection of two seemingly distant words. One is microplastics, the chemical curse of our century, and probiotic metabolites, the quiet molecular allies gifted by nature. Why we need to emphasize chemistry? Because the challenges of microplastics is rooted in chemistry. Their persistency comes from the strength of carbon-carbon bonds. Their toxicity arises from additives, leakages, and surface chemistry. Their global spread is driven by interactions at molecular and interfacial levels. And yet, we shall see chemistry also light the path forward. The very principles of binding, catalysis, degradation, and detoxification can transform this crisis into an opportunity. If we harness not only synthetic chemistry, but also biological chemistry through probiotics, let us remember science is not merely the art of analyzing molecules. It is the power to reimagine them for the service of life. As we begin this concluding session, let's commit to carrying this spark into our teaching, our research, and our mentorship, so that invisible battle against microplastics may one day become a visible victory for humanity and the planet.
Sir,
The screen is
sorry
not
for the
visible.
interruption.
No,
I think if it is possible, share any presentation, sir.
Yes, ma'am. Hope it is visible now.
Yes, sir. Yes, sir. You can continue, sir.
Yes, thank you. Yeah. Over 400 million tons of plastic are produced annually. The majority ends up as microplastics, defined as plastic fragments smaller than 5 mm. Unlike cellulose or starch, these polymers resist hydrolysis because of their nonpolar carbon-carbon backbones and high molecular weight environmental stress like UV and mechanical wear breaks them into smaller pieces, but never into harmless monomers. Today, we find microplastics in oceans, soils, drinking water, air, even human blood and placenta. The urgency is crystal clear. We are not talking about distant pollution. We are talking about molecules in our bloodstreams. The invisible has become unavoidable. This is where chemistry teachers, researchers, and mentors come in. We must lead the scientific dialogue. So the marine chemist Raquel Carson reminds us the human race is challenged more than ever before to demonstrate mastery, not over nature, but of ourselves. Colleagues, if there is one truth in education, it is this: faculty are force multipliers. Every lecture we give is not just information transfer, it is seed of imagination planted in young minds. Think of it, one classroom discussion on polymer chemistry could inspire a student to ask, can this bond ever be broken enzymatically? One lecture on oxidative stress could spark research into antioxidants that counter plastic toxicity. One seminar on catalysis could trigger the design of next PETase variants that digest bottles instead of filling landfills. The real goal of this faculty development program is not only deepen our knowledge of microplastics as pollutants, but to equip with the tools of inspiration, because solutions of microplastics will not come from a single laboratory or a single paper or a single experiment. They will come from generations of scientists who are sitting today in our classrooms, waiting to be ignited by the way we teach chemistry. And that is our true power as a faculty, not just to analyze molecules, but to inspire molecular revolutions through our students. Yeah, when it comes to the objectives of this lecture, chemistry of microplastics, structures, additives, pathways of toxicity, probiotic metabolites, their molecular arsenal, mechanism of interactions, binding mechanisms, degradation mechanism, and detoxification, applications from gut health to environment remediation, food and pharma. By the end, I hope you will feel the same conviction that I do, that chemistry can transform a crisis into a challenge and a challenges into opportunities. Yeah. So repeatedly, the definition is appearing. When we talk about microplastic, let us not reduce them to just small plastic pieces under 5 mm. That's a book definition. For us, as a chemist, as educators, there are something deeper. Molecules of immortality, fragments of our industrial arrogancy. Consider this: every shampoo bead, every degraded PET bottle, every fishing net fiber eventually becomes a mobile particle of chemistry, a synthetic polymer cut into invisibility but never erased. What gives them this immortality? The very chemistry we once celebrated. CC backbones, so stable, they resist natural enzymatic cleavage, hydrophobic surface that defy water and microbial attacks, additives that leach slowly, extending toxicity long after the parent material is gone. So when we define microplastic, let us define them not by size, but by their chemical destiny. Plastic never die. They incarnate into smaller and smaller fragments until they become part of the soil, the sea, even our cells. Let us look at the molecular skeletons behind the plastic crisis. Each polymer is not just a material, it is a chemical personality. Polyethylene ends chains of methylene, chemically inert, hydrophobic, almost invisible to natural catalysis, a material simplicity yet nightmare of persistency. Polypropylene, a methyl branch on the backbone, adds to crystallinity and strength. What engineers call durability, ecosystems call indigestibility. PET aromatic rings stitched with ester linkages. Those esters are weak points, but surrounded by the rigid benzene rings, making cleavage rare in nature. PVC, a CCl bond, deceptively stable in polymers, but releasing chlorine-based toxins, but degrades a single substitution that rewrites the entire toxicological story. Polystyrene aromatic rings, dangling like chemical hoops, interacting with lipids and membranes, making it more than a pollutant, a molecular trespasser inside cell. Now add to this backbone cocktail or additives or phthalates, bisphenols, frame retardants, heavy metals, all this. So every microplastic fragment is not a simple polymer. It is a multi-component chemical entity with the fingerprint of toxicity. Then what is the environmental fate? Microplastics are not static particles. They are chemical travelers moving across boundaries that nature never intended them to cross. In soil, their hydrophobic backbones act like sponges, absorbing pesticides, hydrocarbons, and heavy metals. In oceans, microplastic float or sink depending on polymer density. In the air, light white fibers of polypropylene and polystyrene rise and drift. This is why I say from soil to stomach, from air to artery, microplastic respect no boundaries. Their fate is dictated by interfacial chemistry, adsorption, partitioning surface energy. And because these interactions are universal, microplastic infiltrate even ecosystem and every body. Friends, this is the haunting beauty of chemistry. It explains not only how plastic are made, but also how they travel, persist, and transform into ecological trespasses. Yeah, when it comes to the human and ecotoxicology, once inside the body, microplastic interact at the molecular level. Surface always generation, oxidative stress lipid peroxidation, mitochondrial dysfunction, impaired energy metabolism. It works on endocrine disruption, so from leachate, phthalate, and BPA. Neurotoxicity from plastic associated with heavy metals. Studies now detect microplastics in lungs, blood, placenta, breast milk. This is not abstract pollution. This is chemical invasion of our physiology. As a chemist, we must emphasize toxicity is simply chemistry gone astray. Then what is the knowledge gap? Here lies the most uncomfortable truth. Our chemistry, so powerful in creating plastic, has been remarkably weak in unmaking them. Degrading of plastic is painful, very slow. UV and oxidation only scratches the surface, leaving the fragments that are even more dangerous. Detoxification is poorly mapped. What happens to phthalates, BPA, as they leach and interact with the biology is still full unanswered questions. Conventional solutions, pyrolysis, thermal cracking, advanced oxidation, yes, they break bonds, but at an enormous cost, high energy, toxic byproducts, or limited scalability. So we started at a paradox. The strength of carbon-carbon bond that gave plastic their utility is more barrier that resists every conventional chemistry we throw at it. And this leads us to the fundamental question for the next century. When synthetic chemistry struggles, can living chemistry succeed? Can enzymes, can metabolites, can other microbial pathways evolved over billions of years find cracks in the armor of synthetic polymers? This is the pivot of our discussion, moving from the limitations of industrial chemistry to the possibilities of biological chemistry. From plastic as immortal molecules to microbes as their unlikely challenges. Yeah. Coming to the probiotics, as you all aware, probiotics are defined as live microorganisms which, when administered in adequate amounts, confer health benefits to the host. From a chemical perspective, probiotics are metabolite factories. They secrete acids, they secrete enzymes, they secrete biosurfactants and sticky polymer, all small or macromolecules with reactivity. Genera like lactobacillus, Bifidobacterium, Saccharomyces are not just gut microbes, they are biochemical engineers. This is the bridge plastic, present persistent synthetic chemistry. Probiotics represent adaptive biological chemistry. Let's see how one can confront the other. Yeah, what are the probiotic metabolites? So there are organic acids, lactic acid, acetic acids. These low pH creating the unfavorable conditions for pathogens. Chemically, they also chelate metals and destabilize hydrophobic bonds. Enzymes like esterases, proteases, and glycosidases, these are catalysts cutting bonds in xenobiotics and potentially in plastics. Biosurfactants, which are amphiphilic molecules like lipopeptides and glycolipids, they reduce surface tension, altering hydrophobic surface plastics. When it comes to the EPS, high molecular weight sugar polymers, they are sticky, forming hydrogen bonds and van der Waals interactions with pollutants, including microplastics. Each metabolite is not random. It is a chemistry in action and chemistry that can engage with the synthetic polymers. Yeah, beyond the gut health. Most people associate probiotics with gut health, but chemically their range is far wider. Lactobacillus species bind arsenic through hydroxyl and carboxyl groups on the EPS. Bifidobacterium neutralizes pesticides by enzymatic cleavage. Saccharomyces absorbs cadmium and leads via its cell wall polysaccharide. If these microbes can toxify metals, pesticides, why not plastics? See here, one example is there, so which is published as a news in Current Science Reports, and it is from our Budolas Institute of Life Sciences. So we are able to detoxify cisplatin and its side effects in zebrafish model. And it has become a landmark research of India and published in the Current Science. So if we are able to make cisplatin all other, then why not microplastics? That's our intention. Yeah, what's the opportunity? So here's the hypothesis: probiotics as molecular allies against the plastic. So mechanisms that consider it binds EPS and biosurfactant attaching to the plastic surface, and it helps in the degradation by enzymatic cleavage of ester and amide bonds. It helps in detoxification by transforming the additives into less toxic metabolites. This is not a war of machines or reactions. It is a war of molecules. For us as a faculty, this is an opportunity guiding the students to explore how life's chemistry might solve the humanity's chemical waste. When it comes to the binding mechanisms, every great reaction begins with contact, and in the case of probiotics and the plastics, that contact is binding. Probiotics deploy their EPS and cell surface proteins and decorated with hydroxyl, carboxyl, and amine groups. These functional groups engage with the plastic in their distinct chemical language. Hydrophobic interactions with the inert CH2 backbones of the polyethylene and polypropylene. Electrostatic interactions with changed additives embedded in PVC or sterile-based plastics. Hydrogen bonding with polar oxygen sites in PET and nylon. So scanning electron microscope confirms it. Plastics, once through barren, becomes colonized landscapes of microbial biofilms. Yeah. Now coming to the biosurfactants and surface modifications. Binding alone is not enough. the fortress of plastic must be weakened. Here entered the biosurfactants. These amphiphilic molecules, rhamnolipids, or lipopeptides, or sophorolipids, act as molecular sebators. Their toxicity tails embedded into polymer surface, while their hydrophilic heads interact with water. The result, reduced hydrophobicity, increased wettability. In thermodynamic terms, biosurfactants alter the Gibbs-free energy of interfaces, lowering the barrier that prevents enzymes or water molecules from accessing the polymer. Think of them as surface chemists in action, rewriting the rules of interaction. A polyethylene fragment, once slippery and untouchable, suddenly becomes a site open for the catalytic attack. This is why biosurfactants matter. They don't destroy the plastic directly. They prepare the battlefield for enzymes to strike. Then coming to the enzymatic degradation, how the most relevant assigns enzymes. Take petase, discovered in Ideonella ursaciensis organism, which is surgical precision. It cleaves the ester bonds in PET, releasing terephthalate acid and ethylene glycol. What high temperature pyrolysis demands hundreds of degrees Celsius, petase transform at ambient temperature in water with execute selectivity. Other microbial enzymes, cutinases, esterases, lipases, attack esters, amide linkages in synthetic polymers. To me, enzymes are molecular scalpels, precise, efficient, eco-friendly. They do not transform, they do not burn, they do not corrode, they simply cut the right bond at the right place. And here is where imagination ignites. What if we engineered probiotic strains to secrete these enzymes in the gut or in biofilters? Could we create the living plastic chewers? That is not science fiction. This is chemistry merging with the synthetic biology. Yeah, now coming to the detoxification additives. But the plastics are never just polymers. They are cocktails of additives, and these are often more toxic than the backbone. So phthalate mimic hormones, BPA interface with the endocrine pathways, frame retardants and heavy metal persist and bioaccumulate. Probiotic chemistry does not stop at the polymer. It also engages these hidden passengers. Their enzymes, dehydrogenase, oxidases, and reductases transform functional groups. BPA derivatives oxidized into less estrogen compounds, phthalate hydrolyzed into less toxic monoesters. This is detoxification at the molecular level. A toxic group transformed into biological mimicry neutralized. Thus, probiotics don't merely fight the visible polymers, they clean up its invisible chemical anchorage. When it comes to the synergistic pathways, now let us see the symphony as a whole. EPS binds plastics, which anchoring microbe to pollutants. Biosurfactants weaken the surface, which altering the hydrophobicity. Enzymes cleavage the backbone. So breaking the polymers into monomers, detox enzymes neutralize additives, reducing the toxicity. This is not one pathway, but cascade, a network of interactions where each molecule prepares the stages for the next. The systems chemistry, we know that cooperation outperforms isolation. Binding without biosurfactants is weak. Enzymes without binding are inefficient. Detoxification without cleavage is incomplete. But together, they form a molecular relay race, turning persistence into vulnerability and vulnerability into degradation. This is chemistry's greatest lesson. Its power is magnified not in isolated reactions, but in synergizes the change the fate of matter. When we see some studies, theories inspires curiosity, but evidences ignites conviction. Let us look at real-world case studies where microbes show their chemistry in action. So Lactobacillus rhamnosus, its EPS rich in hydroxyl and carboxyl group from stronger hydrogen bonds with the BPA, bisphenol A, a compound once feared for the estrogenic mimicry. It's literally trapped and neutralized the microbial polymers. Another bacteria, Biofacterium breve, equipped with the hydrolysis. This probiotic can cleave the phthalates, which is used in the drug coating, and breaking down diesters into monoesters, molecules with significantly lowered the endocrine disrupting potential. This is textbook organic chemistry happening in a real cell, living cell. And Saccharomyces cerevisiae, a yeast we often associate it with bread and wine, but chemically it is far more versatile. Its cell wall polysaccharide absorbs both microplastic fragments and heavy metals, simultaneously detoxifying two classes of pollutants. Each of these examples is not just biology, it is applied chemistry, proven as a microbial scale. The larger message is microbes are not passive consumers of nutrients. They are active chemists of the biosphere, writing, breaking, and transforming molecules in ways our laboratories are only beginning to imitate. And if lactobacillus and other organisms can already show their promises, imagine what engineered or consortial probiotics could achieve. These case studies are not endpoints. They are starting points for the chemistry of tomorrow. Yeah, definitely there will be the challenges and the gaps. Every promising story must also face its hard truths. In vivo validation is scarce. Most evidence comes from the controlled lab studies in flasks, petri dishes, and microcosm. Their complexity of the human and the human gut or a river ecosystem still challenges these findings. Plastics are chemically diverse. Polyethylene, polypropylene, PET, PVC, polystyrene, each has a different backbone, polarity, crystallinity, and additive profile. No single engine, no single pathway can conquer them all. Environmental variability is relentless because pH, temperature, salinity, oxygen, all changes the activity of microbes and their enzymes. What works in a lab may stumble in a landfill or in the ocean. But let us not see these as failures. These are all open frontiers. They remind us that solutions to microplastics will never come from one discipline alone. The future will be written when polymer chemists decode bond weakness, microbiologists discovers new enzymatic pathways, toxicologists tracks detoxification products, engineers design scalable systems to apply them. Our role as a faculty is to inspire these interactions and this integration, to tell students, don't stop at the boundary of your discipline. Cross it, collaborate, and create. Because the microplastic problems is not a problem of chemistry, biology, or engineering alone. It is a problem of boundaries, and boundaries can only be discovered by collaboration. What's the gut health applications? Let's start with some intimate laboratory, that human gut. Every day, humans ingest thousands of microplastic particles through food, water, and even air. These microplastics travel through the gastrointestinal tract, where their hydrophobic surfaces may absorb lipids, proteins, and bile salts, potentially disturbing the gut chemistry. Now imagine probiotics here. EPS from lactobacillus can form hydrogen bonds and van der Waals force interactions with the polymer fragments, trapping them in mucus layers. Biosurfactants alter the surface tension of plastics, reducing their adhesion into intestinal epithelium. Enzymes secreted by the microbes could hydrolyze plastic additives into less toxic metabolites. Organic acids lower the pH, preventing leaching the some harmful additives. The result, yes, plastics could be sequestered and excreted rather than absorbed into the bloodstreams. This is the perfect example of translational chemistry. Basic molecular interactions becoming a medical strategy. Imagine the day when probiotic capsules are marketed not just for digestion, but for plastic detoxification. This is preventive medicine driven by chemistry. Yeah, when it comes to the environmental bioremediation, now let's zoom out from gut to the environment. Wastewater treatment plants already use microbial biofilms to degrade organic pollutants. Why not tailor with for plastics? EPS acts as like a molecular Velcro, capturing microplastic fragments. Biosurfactants reduce hydrophobicity, making plastic easier to degrade. Enzymes like PETase, cleavage, they cleave the polymer backbones into small monomers. Imagine engineered biofilters seeded with probiotic consortia like lactobacillus and other bacteria, pseudomonas and others like pseudomonas for the biosurfactants. All these together, they form a living chemical sponge. The best part is this is eco-friendly, sustainable, scalable. Unlike harsh chemical oxidants, probiotics operate under mild conditions, with water as the medium. For us as a faculty, this is a fertile ground for interdisciplinary student projects. Chemistry meets microbiology, engineering, and environmental science. When it comes to the food industry application, the food industry is under pressure for clean, label, sustainable solution. Here, probiotics offer an exciting frontiers. Fermented food enriched with probiotic strains could bind and neutralize plastic additives like phthalates and BPA and leach from packaging. Functional foods could be fortified with the engineered strains, chemically equipped with the surfactants or detox enzymes. Cheese, yogurt, these could become more just nutrients, but protective foods. Think of chemistry here. Amino, hydroxyl, and carboxyl groups in microbial polysaccharides, binding contaminants, while enzymes dismantle xenobiotics. This is the chemistry driving innovation in food safety. It goes beyond safety. It becomes a value-added promise to the consumer, food that actively defends against plastic toxicity. Yeah, here the futuristic vision, probiotics as a engineered molecular machineries. Synthetic biology can insert genes for the protease, cutinases, and biosurfactants synthesis into common probiotic strains. Capsules containing these engineered microbes could survive gastric passage, colonize the gut, and degrade the ingested plastic in situ. Designer microbes could be formulated as nutraceuticals, delivering plastic detox as a part of daily healthcare. The analogy is sticking. In the 20th century, antibiotics becomes our defense against the microbes. In the 21st century, the new medicine may be anti-plastic biocapsules. And behind it all lies chemistry, the precise breaking of ester, amide, and aromatic bonds by engineering enzymes. This is not a science fiction. It is a logical next step, molecular medicine. Now let's bring this back to us, faculty. We are not merely teachers or formulas. We are bridges between molecular knowledge and societal problems, between students' curiosity and future innovations, between laboratories and policies. As mentors, we must encourage students to design real-world applications like biofilters, functional foods, nutraceutical probiotics. As advocates, we can push the policies that recognize probiotics as a part of environment management and public health strategy. This is where chemistry teaching becomes transformational. It's no longer about exam preparation. It's about preparing the next generation to clean the planet. Let's close the session with vision. Microplastics, once through indestructible probiotics, one limited to gut health, together emerging as a molecular evolution. The chemistry of one century's crisis could become the chemistry of the next century's cure. And who carries this forward? You do. the faculty, the torchbearers. In our classrooms, in our labs, in our mentorship, the seeds of this revolution can be planted. To summarize our entire journey, hazard, microplastics, persistent synthetic polymers with the toxic additives, alleles, which are probiotics, microbial chemists, producing acids, enzymes, EPS, and biosurfactants, the mechanisms, what we learn, binding, degradation, and detoxification. And application comes gut health, environmental remediation, food safety, and pharmaceuticals. This is the framework of hope, where chemistry becomes the solutions, not the problem. Yeah, we are ready to collaborate as a life sciences researchers, and we have all the good facilities. If anyone have the thrive, anyone have the quest to do research on these topics. Science thrives on questions. Here are a few that could guide next decades. Can probiotics truly reduce plastic burden inside humans? Which metabolite is the most powerful? EPS for the binding, enzymes for the cleavage, or biosurfactants for the surface modification? How can we scale this from lab to wastewater plants, or food to industries and healthcare? Each of these as a research proposal, maybe as a PhD thesis, maybe as a startup idea. Unanswered questions are not obstacles. They are invitation. Yes, ma'am. That is the beauty of
summarize.
Yes, ma'am. Yeah, dear colleagues and participants, as we come to the end of this faculty development program, let us pause and reflect. Over the past days, we have examined microplastics as emerging pollutants, their chemistry, their pathways, their analytical tools to detect and monitor them. We now conclude with a hopeful lens, the possible that nature itself, through probiotic metabolites, may provide molecular strategies for binding, degradation, detoxification of plastics. Thank you very much, ma'am.
Sir, can you share your email ID, please?
Yes, ma'am. Just is budola@gmail.com. Budola, my name, @gmail.com.
Sir, your name and then gmail.com, right?
Yes, ma'am. And Dr. Saraswati will provide everything for you, ma'am. Mail ID and the website and everything, all the details, definitely.
Okay, sir. Thank you
to all the
so much.
participants. Thank you, ma'am.
Yeah, thank you, sir. I extend my heartfelt thanks to Dr. Budola Vishwanath for his thought-provoking session on the chemical interactions between microplastics and probiotic metabolics. Your interdisciplinary approach opened new scientific dimensions. I also thank all attendees for joining this session, enriching learning journey. Thank you once again, sir, for your effective presentation to need endless research on microplastics. Yeah, thank you, sir. Thank you very much.
Share the slide to all of us, sir.
Sir, please, sir.
But I request to please share the slide. This slide is very wonderful to us.
Definitely, sir. Definitely. I'm going to make it. Sure, sir.
Thank you very much, sir.
Thank you, sir.
Yeah, now I request Dr. Venkatalakshmi Madam to give her feedback for the overall FDP sessions.
Yes, ma'am. Thank you for granting me this opportunity. Good evening, KPRIT COE Chairman Sir Dr. Kumar Prashant Reddy Garu, Vice Chairman Sir Dr. Prashant Reddy Garu, Director KPRES means for both the colleges KPRIT and KPRIT COE Dr. Sudhir Prem Kumar Sir, KPRIT COE Principal Sir, Vice Principal for both the colleges, KPRIT and KPRIT COE, Dr. Srinath Kashyap Sir, Resource Person Sir, Resource Person Dr. Vishwanath Sir, and Dr. Saraswati Madam, organizing team, and my fellow faculties. Very good evening to all. I am Dr. K. Venkatlakshmi, Assistant Professor of English, KPRIT. This AICTE sponsored 6 days ATAL Faculty Development Program on microplastics as emerging pollutants, analytical and monitoring perspectives, which was started on 22nd of this month, and it's an awful journey up to today. I am very little bit feeling not sad, just I am going to leave this program. No, all we are missing this program, and as a feedback, I want to share microplastics no longer just as an environmental concern, but a processing global challenge demanding immediate attention from both the scientific and policy making committees. It is impacting ecosystems and human health. Through research, innovation, and collective responsibilities, we can move towards effective solutions and a sustainable future. Thank you, one and all. Thank you, Saraswati ma'am and other organizing team for granting me this opportunity. Thank you, one and all.
Thank you, ma'am.
Okay, cut చేయి Kusma, please.
Ma'am completed. Thank you, ma'am. Saraswati ma'am, Dr. Saraswati ma'am.
Thank
Hello.
you, ma'am, for your positive feedback.
Thank you,
So,
ma'am.
let us invite Dr. M. Sudharani, madam,
Madam.
to give her feedback.
Okay, madam. Good evening, everyone. This is Dr. Sudharani, Associate Professor, Guru Nanak Institutional Technical Campus.
Prakash Babu.
Madam, is it audible?
Audible.
Yes, ma'am, it is audible. It is audible.
Okay, ma'am. Good evening, everyone. This is Dr. Sudharani, Associate Professor, Guru Nanak Institutional Technical Campus. I am extremely happy to give my feedback on online FDP conducted by KPRIT College and organized by Dr. Saraswati ma'am. Saraswati ma'am maintained excellent coordination and smooth execution. So this FDP encouraging continuously learning and professional growth. All the sections were motivating and inspire innovation thinking. This program helps in bringing the gap between the theory and the practice. So here, this FDP helped me gain new insights into teaching and research methods. So a resource person explained about that microplastics are emerging pollutants widely present in the environment, and their detection requires advanced analytical techniques and systematic monitoring to understand and control their impacts, explained by resource person very well. So once again, thank you, Madam Saraswati Madam, giving this opportunity to participate in this FDP. Thank you, Madam, once again.
Yeah, thank you, ma'am. Thank you for your excellent feedback. If anybody, Pratap sir.
Yes, ma'am. Good evening.
Yeah.
I would
Yeah.
like to share the words.
Yeah.
Good evening, everyone. This is
Nice to
Sumani
you.
Sai.
Yeah. Nice to
Shall I
see
proceed?
you.
Hello,
Yeah.
ma'am. Hello. May I talk?
Yeah, you can, sir. Manish Kumar, sir.
Oh.
Maybe.
So I am Dr.
Yeah.
Manish, working as assistant professor in Central Institute of Petrochemical. Here we deal with the plastics testings, and we taught the student of plastic. So it is very helpful for me through this FDP portal. Now all the sessions were very nice and insightful. So I thank you and congratulate to these all coordinators. Thank you, ma'am.
Thank you, sir. Thank you. Shaini, ma'am, will you?
Yes, ma'am. Yes, ma'am. Good morning. Good evening, everyone. This is Suman Sani, Assistant Professor Chemistry from Chandigarh Engineering College in JD Campus, Mohali, near Chandigarh. So it gave me an immense pleasure to share my feedback on this online FDP. So first of all, I would like to congratulate all the coordinators and team for the successful completion of this FDP. So it was really a great experience to hear from all the renowned experts as speakers of this FDP. They all enhance our knowledge on the major problem of our environment, which was the microplastic is emerging pollutants. So various types of, in this FDP, we learn about various types of sources and environmental impacts of microplastics were discussed and explained in a very easy way through PPTs, and very effective diagrams were there. So in this FDP, light was also thrown on the analytical and monitoring perspectives on microplastics. And knowing about various types of methods to degrade microplastics, like physical, chemical and biological degradation of microplastics, was one of the very interesting topic that we came to know how microplastics can be degraded through various types of enzymes. And we also least but not the last, we also learn about the various health hazards risk associated with these microplastics. So we have learned, we are learning a lot from this session from the past 5 days, and we can utilize this knowledge in our research work also, and we can even give this knowledge to our, being a faculty, we can exchange our knowledge to our students so that they can be as told in this FDP. We can bring good scientists, young scientists for they can bring a good solution to this microplastic degradation, and which is a very harmful for our health also and for our environment also. So in today's session was also very interesting. Enzymatic green catalysts were discussed. So it was really, it was a really knowledgeable session of this day also, which was the concluding session. So I congratulate to all the coordinators once again. So overall, it was an excellent FDP, online FDP. In which offline is always excellent, but online was also very effective and learning. So one of the best FDP, I must say. So thank you so much, and I wish you all the best to all the team of this college and coordinators. And I wish in future also such FDPs will be organized with this great zeal. Thank you, ma'am. Thank you so much.
Thank you, ma'am. Now I'm inviting our principal, college, KPRIT College of Engineering, to give vote of thanks for all the sessions. So, sir,
Madam,
kindly join with us to give vote of thanks in valedictory session.
good evening to one and everyone. This is Dr. K. Srinivas Reddy, Principal of KPRIT College of Engineering. It gives me great happiness to witness the successful completion of this ATAL Faculty Development Program. Over the past few days, we have learned many new things, shared ideas, and gained valuable knowledge from our respected resource persons. And also, my sincere thank to AICTE ATAL Academy for giving our institution this opportunity. My heartful thanks to all the experts who guided us with their insightful sessions, and to the coordinators and organizing team for their dedicated efforts in making this program a grand success. Is it audible, sir?
Yes, sir, audible, sir.
Our special thanks to Dr. Uma Maheshwari, Madam, Vice Chairperson, APSHE, for kindly accepting our invitation and gracing the ATAL Faculty Development Program as the guest of honor. Her valuable contribution for guest of honor for this FDP and words of encouragement greatly motivated the participants and added the immense value to the program. My sincere thanks to Coordinator Saraswati Madam, Co-Coordinator Nagendra Sir, for organizing this ATAL FDP program a grand success. Most importantly, I appreciate all the participants for your active involvement and enthusiasm. I am confident that the learnings from this FDP will enrich our teaching, research, and professional growth. With this, and also my sincere thanks to our management for providing necessary facilities to organize this event. With this, we formally conclude the program. I wish you all the best in your future endeavors. Thank you. Thank you very much. Madam, Saraswati Madam.
Yeah, sir. Thank you, sir.
Please
Thank you for
continue, madam.
your wonderful speech. So, thank you, dear participants. Just take the first feedback. Thereafter, take at exactly 9:15 exam in your portal. Kindly attend the exam. So, followed by feedback. Everything is available in your registered portal. Kindly open with your username and ID. Then attend the exam. If any problems, if you will face, kindly let us know. We will share in other way. Thank you one and all to made these sessions are a grand success. Thank you.
Thank you, madam.